All right, here we go. This one is a fun little mini lab or demo where we show the data actually work out or not in class. And so this year we'll just do it as a DDD. And what you have here is you have a base, and then this is an upper platform, and there's an axle that you can't see going through the middle, so that this top layer can spin. And I'm reminded of something called a lazy Susan, if you know what that is. Some restaurants will, at a big round table, will have the inner part of the table can spin, so you can move food around from one place to another. But this is just a big table where the top of the table can spin. Maybe you saw it in the classroom. And I've taped a little Velcro adhesive on this side on the table, and then on the other side on this Bluetooth speaker, so that this Bluetooth speaker is attached pretty strongly to the spinning tabletop. And then we spin the top, and then someone over here somewhere at a distance horizontally from it can put up a microphone, and they can see that the tone, you could actually hear it yourself if you have good hearing, good tones of listening. But definitely with the microphone and then a little bit of analysis, you can see that the frequency that you observe as the speaker is going away from, let's say that it's here, for the speaker going away from you. So sorry about that interruption, but as the speaker goes away from you here, then you'll hear a lower tone. And then as it spins around and then as it's coming towards you here, you'll hear a higher tone based on how fast it's actually moving away from you and towards you. So in this question, I've given you these two frequencies, and so we can look and see this one's at 65, this is 64. So 64 is the lower note, and this lower note would be as the speaker is moving away from you, assuming you're over here somewhere. And then as it comes around and now as it's coming towards you here, then as it's coming toward you, a higher tone, and so that would be this one. And then when it's moving horizontally, either this way or this way, then you'd have the tone that's in between those at 6,500. So we have the 6,500, then it goes up 40, if it goes down 40, approximately based on whether it's moving away from you or whether it's coming towards you. And then the question is asking you to find the radius of the circle. But in order to do that, we've given the period of the rotation. So in order to figure out the radius, we'd have to figure out the speed. So we'll use the Doppler effect and solve for the speed, actually, instead of solving for the frequency. And then once we have that, we can get the radius for that. Then in B, a little throwback question here, because I use Velcro on here, because otherwise the speaker just goes flinging off when you spin it. So there's a standing coefficient that's very strong here, holding this speaker onto the table as it spins. And it's standing, even though this thing's moving, nothing's sliding, like the speaker stays at the same point on the table. So it's standing, and it's a pretty big coefficient of standing friction, because otherwise this thing would go flying off in a straight line instead of going in a circle. And then finally, C asks, explain what another observer, Sue, who is, Bob was at 4 meters, Sue's 8 meters away, will hear. And I guess I'll do that one first since we're here. It still would be going towards Sue at the same speed as it's going towards Bob. So they're going to hear the same frequencies. So they'll hear the same frequencies. The only difference would be because Sue's twice as far away, Sue would have twice the distance. So 1/4 of the energy would be getting to her ear. So she'd have 1/4 the intensity. Not decibels; those are this weird logarithm scale, and decibels are not in the syllabus. So you might have heard about decibels for rock concerts and hurting your hearing and stuff, but that's not the scale we would use. We would just say intensity in watts per meter squared would get 4 times less for Sue because she's twice as far away. So let's do A and B then, since we've already done C, and take a look at what happens here. So it looks like the first thing we need to do is realize that it's the moving source. Remember, because it's a speaker that's spinning around in a circle. The source is moving. So we're going to use this equation. And we can either use the plus or minus depending on which numbers we decide to pick. So for this F, I'm putting in the 6,500. That was the number in between them. And then for F prime, what we hear, I'm using the bigger number. So this must be when it's coming towards us. And if it's coming towards us, we're going to use a negative there. And this U is what we don't know. So we have to solve for U here. And you have this algebra here to do. So let's see how we're going to get U by itself. So if we do a little sort of cross multiplying kind of idea where this is going to come down here, this term with the subtraction is going to go up there. So I've got this 6,500, this 6,540 came underneath. This whole term here, right, is up here now. I didn't put parentheses around it, but it's the same term. And then we solve for that, and we get 342.89 for this. And then we need to bring U over here and that over there and subtract, and we get 2.1 meters per second. It's not amazingly fast, but it's fast enough that if this thing wasn't Velcroed on there pretty good, it would not stay on the table. And it's fast enough that you can hear a frequency change there to a certain degree. Really, you'd want to spin it even faster if you wanted to see a better thing, but maybe you'd want to like actually duct tape it on or something. But in any case, let's see what the standing coefficient of friction would have to be. Or actually, the radius was the first question. So we have V equals 2 pi r over t, and solving that for r, we're going to get VT over 2 pi, plug and chug there, and we get a radius of about 20 centimeters, which is about right if you've seen this thing in my room. Anyway, next we go to the coefficient of standing friction. So a little throwback here. We got the centripetal force equation is mv squared over r, and the centripetal force being caused by friction only. And this is standing friction, so we're using this inequality. But the question asks for the range of coefficients. So we'll just find the coefficient that barely works and then think about which direction we want to go. So we set the force of friction equal to centripetal force because that's what it is. The frictional force is acting centripetally on that Bluetooth speaker. So we get mv squared over r equals mu normal force. The normal force is mg. And m's cancel. We don't care about the weight of the Bluetooth speaker itself. And solving for mu, the g goes in the bottom there, plug and chug with our numbers. We get a coefficient of friction about 2.25. If you recall, those typically are like 0.3 or 0.5 or stuff like that. So it's a pretty big coefficient. And then I'd say or more, because you can make it even more attached if you made it even stickier. So it needed to be pretty sticky for this to work out. Sue and Bob hear the same frequency, but 4 times less intense since she is farther away. Yeah, she's the one that's farther away. So there you go. Interesting question. Please notice that if Bob or Sue were really close, when they would hear those frequencies wouldn't be exactly halfway through the rotation, because you think of a tangent line pointing, let's say there's another person here, let's say Phil is right here, and as this is spinning, only when it's aimed straight at Phil would it hear this high, and only as it was going away would it be this low, and there'd be a long time before it came back again. Where the farther away you are, it gets closer to the edges of when you would hear it. But no matter where you are, you actually hear the highest frequency, and then the lowest frequency takes a little less than a full rotation of time, a little less than half, I should say, of the full rotation. And this has been questions like this have been an IA or an extended essay. This has been the basis for a couple of those that have been turned out pretty well in my career. Anyway, that's our last one for today. So I hope that helped you understand the Doppler effect and get a feeling for how really straightforward 9.5 is in a lot of ways compared to 9.4. But still some interesting concepts and certainly important concepts, especially when it comes to astronomy and understanding our universe in terms of the red shifting nature of the universe. Anyway, see you soon. And I think we're having a meeting where you could ask some questions on these if anything's still bugging you about any of these problems that we're working on. So see you then.